Okay, let's take one more look at polar graphs. As a reminder of some of these more basic principles, that x equals r cosine theta, y equals r sine theta. We can say that at any point the x and y coordinates form the Pythagorean theorem with that, and we can say that tangent of the angle, of course, is always just y over x. And then we have the calculus ones, right? So we can look at dy dx, which is and always will be the slope of the graph. The slope of the graph is dy d theta over dx d theta, which is taking this derivative with respect to theta and this derivative with respect to theta. We can look at dr d theta, which is just taking the derivative of r with respect to theta. We could look at dr dt if we had d theta dt, so that's dr d theta times d theta dt. We could look at the arc length in polar, which is a derivation of basically the Pythagorean theorem, integrating from one theta to another theta. We can find the area in polar, which is really just algebra 2. It's the summation of a bunch of sectors where each sector has a really small d theta. We can find the intersection of two polar curves by just setting the r values equal to each other and finding the theta that happens. Okay, so we can do all of these things. We can use dr d theta to find max and min distances from the origin, right? Because that's what r is. It's the distance you are from the origin. And then we can draw a bunch of graphs. So let's just look at some of these curves, right? So all of these things are defining some polar curve, and we're finding certain properties of them. But let's look at some curves. So how about r equals 2 plus 4 cosine theta? Okay, and let's look at what that's going to look like. Okay, so you can see that at the beginning, when theta is 0, we're all way over here at 6. So this is where we start. Remember, theta of 0 is pointing that direction. Remember, this is 0, pi over 2 pi, 3/2 pi, and then back to 2 pi. Those are the directions you always start in the x-axis, and then we rotate this way. The hard part is when r is negative, and r is going to be negative here because eventually this is going to be bigger than -2, and then r is going to be negative, and when r is negative, you flip it into the other quadrant. So if you were in quadrant 1, then you get flipped down to quadrant 3. So what happens here is that when does this become negative? So when does this get back to here? Because what's going to happen here, think about what cosine is going to do. Cosine is going to do this, right? And at some point, cosine is going to be bigger than -2, and then this r is going to be negative. Well, when does that happen? Well, it happens at 2/3 pi. When theta is 2/3 pi, that's when cosine, that's a reference angle of 60, that's when cosine is -1/2. 4 times -1/2 is going to be -2. That's when it gets back to this value. Okay, so 2/3 pi happens over there. So we're going to go like this. And then when you get back to there, you're there. Now, the rest of this, you should be rotating through this second quadrant, but you're not going to be, because eventually when you get to pi, when this is pi, this is going to be -4, and this is at -2. So when I am pointed in the pi direction, I'm actually at -2. So what I'm going to do is, I'm going to wrap like that. And when I'm in the pi direction, I'm at an r value of -2, which flips me back over here. So all of these theta values produce negative r values, which flip me to there. Okay, and I'm going to continue to be negative all the way until I get to 4/3 pi. So when I get to that angle, so I'm going to rotate back, and then boom, I'm back. Now, after 4/3 pi, then I'm fine again. So then I'm going to cycle through like I should in this, and then right back to there. So that's what this particular curve looks like. Hopefully you can imagine that when r is negative, I'm going to form this internal kind of loop here, because instead of being in the second and third quadrant, I get flipped into the fourth and first quadrant. When this is bigger than -2, this is bigger than -2 from 2/3 pi to 4/3 pi, because that's how the unit circle works, right? That's when cosine is going to be -1/2. Okay, so we can look at stuff like that. We could look at a polar curve like cosine of 2 theta. Okay, and that 2 theta is going to make everything rotate faster. Okay, so when theta equals 0, I'm out here at 1, because cosine of 2 times 0 is cosine of 0, which is 1. And then when do I get back to the origin? Well, I get back to the origin when cosine is 0. Cosine is 0 at pi over 2. But this is going to be pi over 2 when theta is pi over 4, because pi over 4 times 2, right? It's going to get there twice as fast. So you're going to go like this. You're going to go here, and you're going to get there at pi over 4. And the rest of the rotation in the first quadrant is going to get flipped and be in the third quadrant. So you get this for that first quadrant rotation. Again, now I should be over in the second quadrant, but I'm not going to be. I'm still have a negative r value. I'm going to be here, and I'm going to get that. And now I'm back, right? I'm back at 3/4. And then I'm going to go around like this. Hopefully you can kind of get this general idea. That's going to circle like that. And what you're doing is you're graphing cosine, but cosine is going to go way faster than it should. And that's 1, and then that's another. So cosine of 2 theta is actually going to get all the way to here by pi. And so that's that 2 pi. 2 pi is all the way to there. And you can see then that what happens is this first part right here, and then this is that second part. From here to here is from here to here, and then from there to there is this down part, negative. And then I'm still negative, so I'm still flipped. And then I become positive again. See, I'm back where I should be. Now I'm in the third quadrant where I should be, and then boom, now I'm back here. I'm negative, so I'm not in the third quadrant. I'm actually in the first quadrant. I'm negative, I'm in the second quadrant, and then boom, I'm finally back to where I should be. So each one of these, 1, 2, 3, 4, 5, 6, 7, 8, is the same thing. 1, 2, 3, 4, 5, 6, 7, 8. Each one of these humps here correspond to individually one of these things. So that guy right there corresponds to that guy. Okay, this is this next one. This right here is this right here, and you can figure out the angle and the r value. Remember, if r is negative, they're going to be flipped into the other quadrant, and you can kind of just trace through what they all look like. Okay, and we'll look at some more. And as a reminder, these are pretty hard, so you're going to have to take some time to kind of figure out what they all look like. Okay, let's take a look at one where the r value doesn't become negative. So what about 3 plus 2 sine theta? Now in this case, this is never bigger than 3, so r is never negative. These are easy to graph, because if r is never negative, meaning r is always positive, then nothing ever gets flipped into a new quadrant. And so you are where you should be. So when I look at theta of 0, when this is 0, sine of 0, 0, 0, 3, I'm at 3. Okay? So when theta is, if I'm doing a theta r chart in my head, when theta is 0, r is 3. Now when theta is pi over 2, meaning straight up, this is 1, so this becomes 5, so it's going to grow. When theta is back to pi, way over here, this is back to 0, so this is back to 3. So this first part's pretty easy. Let's extend this all the way up to kind of 5. This is going to kind of go like this, to 5, and then back down to 3. Again, not the best drawing I've ever had, but these are both at 3s, right? 0, 3, pi, 3, and this is at pi over 2, 5. So you're higher there. But what happens here? Well, now, what happens to the sine curve? Well, just think about what sine does. Sine does this. That's what we've done so far. And now we have to do this. Now sine's going to be negative, so I'm going to be subtracting from, when I do all the way from pi to 3/2 pi to 2 pi, R is going to be negative, so I'm going to be making, or excuse me, this is going to be negative, so I'm going to be continuously making R smaller, so it's going to dip, and it's going to be the smallest at this value, because at here, this is -1, so this is -2, so this is only 1, so I'm right in here. I'm only at 1 there, and all of these other values I'm subtracting, so I'm going to do something that kind of looks like this, and I get some cardioid type shape. And again, why do I have this sample? Because in these rotations from pi to 2 pi, sine is negative. That whole time I'm subtracting, because this is a negative, so I'm subtracting 3, so my R values are going to be smaller in those regions, where from 0 to pi, this range of the sine curve, I'm actually adding to R and I'm making R bigger. R is its biggest here and its smallest here, right? Biggest and then smallest. And again, you can continue to look at different graphs and what they all kind of do. And again, it's not always the easiest thing to graph these. You're just going to have to use, take some time and do some examples. How about R minus cosine theta? How about that one? Okay, so let's look at that graph. And again, on all of these graphs, we can find the area, we can find the arc length, we can find dr dt, we can find dx dy, we can find the tangent line. We can find those things. We can find the intersection of two graphs, right? We can put this graph on another graph, the same thing. All right. So how about this one? This is going to be another cardioid. It's just going to be, instead of kind of an up and down cardioid, it's going to be a side to side cardioid. So think about theta and r. When theta is 0, this is 1. And so when theta is 0, r is 0. Well, when r is 0, that means you're at the origin, right? It means you have no distance. And then what happens to cosine? Cosine is going to get smaller and smaller. As cosine gets smaller, you start subtracting less and less and less. And when you get to the top, at pi over 2, cosine is 0, so I get to here. So as I rotate through the first quadrant, my R value is getting bigger and bigger and bigger. Okay, so I get to there. And now I get all the way to pi. Well, when cosine is pi, cosine is negative, so I'm going to be all the way out at 2. All right, so that means I get to here. So I'm going to bend this way. Again, I'm going to be subtracting this negative. That's what I'm doing right here. This right here is this region of the cosine curve. I'm subtracting a negative, so my R value is actually getting bigger and bigger and bigger. Okay, I continue to subtract a negative. All right, so my R value is still big that same way. It's very symmetrical there. And then it's going to bend back in. And then when I'm in the fourth quadrant, 3 pi over 2, this is 0, so I'm back to 1. And then as I get all the way to 2 pi, I'm going to go back to 0. And I'm going to come right back in and kind of get a shape that looks like that. And again, on all of these shapes you can do. So again, you can do all of these things however you want. Okay? If let's say I wanted to find the intersection of two curves, let me show you how that would work. Again, the intersection of two curves you have to do on your calculator, but it's not really a big deal. Let's take R equals, theta plus 1, and this is a spiral, and so when theta is equal to 1, R is equal to 1, and so we're right here, and this thing is going to spiral around. So when theta equals 0, R is 1. When theta equals pi over 2, which is like 1.5-ish, well then this is pi over 2 plus 1. R is always theta plus 1. So this is like 2.5. So we're still like right there. And at some point then we're going to spiral and go and get bigger. And if we wanted to find this intersection point, okay, then what we would have to do is we'd have to set 3 plus 2 sine theta equal to theta plus 1 and figure out at what angle the R values were the same. Now, unfortunately, this can't happen in polar coordinates, meaning your calculator can't do this in polar mode. You can't graph both of them and say find intersection. So what you have to do is you have to turn your calculator back into Cartesian mode and let it solve it in Cartesian mode. So now you're graphing as y1 and y2, finding x, but again, x is a number just like theta is a number, and so finding x is the same thing as finding theta. Your calculator can just do it in Cartesian, and it can't for some reason in polar. So go ahead and change it back. Okay?